All right, next we're going to be talking about SN1, E1, E2, and SN2 reactions. To, I guess, understand this, first I will let you know that SN1 and SN2 just basically means that you are substituting a product, while E1 and E2 is elimination. So you basically get rid of a product. So I guess let's say you have a leaving group, so let's just say I. Either E1, E2, because we eliminate this, you only get a double bond, so then in a reaction could end up something like this. Coincidentally, let's say we have a leaving group right here with a nucleophile, same here, nucleophile. Basically, you just replace it with that new nucleophile. And that's kind of like the basis of what an SN difference between SN and E is. However, there are differences between E1, E2, SN1, and SN2. So SN1 and E1 are similar in that they kind of go by a step-by-step plan. They are a unimolecular step. So basically everything happens one by one. Whereas E2 and SN2 are bimolecular step. So everything happens all at once immediately. So now I guess I'll just show you some examples. So like what exactly is an SN1 reaction. So let's say we have a compound like this with a nucleophile, and basically it's a step-by-step process. So we first get rid of our evident leaving group, which becomes now a positive value because the electrons are gone. And by this, we can then determine what's like the most stable step. And from that, then we can add our nucleophile. So then we get a reaction that looks like this. And so you can now label this as SN1 reaction. All right, now we'll do one with SN2 reaction. The type of product does matter, so I'll go over that in a bit after this. But basically everything here happens at the same time. So for the chlorine, it's the leaving group, so it immediately leaves. And while it's doing that, the nucleophile backside attacks it, so it goes from behind. And there we have our new reaction, which just everything happens all at once. Now for our next one, we'll go over an E1 reaction. So say we have this. Oh yeah, my bad. The elimination should be a base, not a nucleophile. Sorry about that. All right, so let's say we have a base, and it's similar to SN1. We first get rid of our leaving group, so then we have a positive carbocation. And from there, we'll decide where the positive carbocation should be before we add our base, which is a double bond. And then after that, once we have a stable section, then we'll have our reaction, which could just be like this. Actually, I believe this, because it's the more stable state. And then for E2, it just all happens all at once. So carbon leaves, and then we're just left with a double bond basically here. So it just becomes something like this. And now we can make a table out of this to get a clear, better picture. We'll start off with our substrates. And for our substrates, you can have a primary substrate, which looks like this. Say I as our basically our leaving group. So this is what a primary substrate looks like. And then secondary looks like this. And then tertiary. And now in terms of what could be done in our reaction, you could have, let's say, a strong base and a weak nucleophile. So this could look something like this, or NaH. And because we have a bulky base in a first degree molecule, this becomes an E2 reaction. Same thing with secondary, it's E2, no matter what, and tertiary is E2. So just remember, for a strong base / weak nucleophile, in every instance, it's an E2 reaction. We have a strong base and a strong nucleophile. So these are like your OH negatives, or basically any oxygen residue that's highly negative. In the primary, it's going to be SN2. And then for our secondary, it's E2, but slightly some SN2 reaction. And then E2 for tertiary. And this kind of makes sense for why it's an elimination here only for tertiary, is because let's say you have a reaction that looks like this. It's very hard for, let's say, the nucleophile to backside attack this simultaneously. The only way you could do this is just through an elimination instead. Now let's say we have a weak base, strong nucleophile. Think of this as mostly like all of your positive, negative charge iodides or sulfurs. That is highly negative. For the primary and secondary, they're both in SN2 reaction. And then in tertiary, it goes in SN1. So only here in the tertiary where you're going to have step by step. And then let's say for weak base, weak nucleophile, it's your water. This one. Any form where oxygen has a full octet rule, there's no negative charge at all. In the primary stage, there is no reaction at all that's ever happening. And then for tertiary and secondary, it's a racemic. So it's basically 50-50 with SN1 E1 for both. And one thing I forgot to mention is that in an SN1 reaction, your solution is racemic. So in both scenarios, let's say you have a reaction that looks like this with H2O or something like that. Both instances, when we eliminate the chloride, you have a positive cation. H2O can attack either side of the designated carbocation. And because of that, we can have a racemic reaction where OH could be in an S or R configuration. And that's typically just for SN1. Since SN2, you already have to go through a backside attack. So yeah, hopefully that was helpful. I would just recommend just looking at this diagram just so that you know what types of reactions there are.